Hi guys, I just wanted to finish up today our PowerPoint on ionic bonding and ionic compounds. So you started naming and writing formulas, chemical formulas, for ionic compounds yesterday in class, and I just want to go through a little more and review about what ionic compounds are. I want to talk a little bit more about these polyatomic ions, and then we're going to talk about properties of ionic compounds. So we know that an ionic compound consists of a metal and a nonmetal, or we could also say a cation and an anion. And we know that the cation is a positively charged element, and an anion is a negatively charged element. An ionic bond happens because we have a transfer of electrons. So just like when we draw those Lewis dot structures, we take one electron away from a metal, and that electron moves actually over to like a nonmetal, like chlorine. So then that way, the cation, or that element, the metal, becomes positive. It becomes a cation, and it has a full outer shell because maybe it got rid of one when it had one valence electron. And then the nonmetal, maybe like chlorine, which needs to gain one. Once it does gain one in its outermost shell, then it becomes stable and it becomes full. So we're following this octet rule, which tells me that I need to have 8 valence electrons on that outermost shell. For polyatomic ions, which I gave you a list of yesterday in class, on this, it looks on your notes, I'm looking at this slide where it talks about polyatomic ions, or ions that are made up of more than one atom. So we know that poly means more than one. We know atomic just means atoms, so we have more than one type of atom. Now, on that list, I want you, we talked about this yesterday as well, but I just want to reiterate that they will act as a unit, which is also discussed here in your notes. So it says that since polyatomic ions exist as a unit, I'm always going to leave that formula the same. So sulfate. Let's find sulfate on your chart, on your little piece of paper. If I were to find sulfate right here, that'd be SO4. And sulfate is SO4 and it has a -2 charge. That means that sulfate will always be SO4. I'm never going to change it. It always acts as a unit. I change nothing about the numbers on it. It will always be SO4. Okay, so it exists as a unit, and that's really important that we know that that's how polyatomic ions work. Now, I gave you a list, and your list I think looks a little different maybe than this one, and that's because on this one, there's some where I feel like you don't need to know them because you'll never use them. In terms of some of these polyatomic ions, I want you to look at, find nitrite and nitrate. So nitrite is NO2 with a -1 charge, and nitrate is an NO3 with a -1 charge. So the only difference between those is that one has one more oxygen than the other one does. So nitrate has one more oxygen, nitrite has one fewer oxygens. Also find for me sulfite and sulfate. So it's kind of following the same rule here because I have nitrite, nitrate, so ites and ates, and then I have sulfite and sulfate. Sulfite has one fewer oxygen than sulfate does. Now find for me phosphite and phosphate. They're in the -3 charges. Phosphite has one less oxygen than phosphate. So if it helps for you to remember these are called oxyanions. And all that means is it's a polyatomic ion where there's an element, and typically that's a nonmetal. Usually a nonmetal is going to bond with oxygen to make a polyatomic ion. But we usually have a nonmetal, and it's bonded to an oxygen or several oxygens. So in this case, we have nitrite and we have nitrate. Always the polyatomic ion that has more oxygen that the nonmetal is bonded to is going to end in 8. So NO3 versus NO2. NO3 has more oxygens because I have 3 oxygens in that one, versus NO2 only has 2. So that means that this one is going to end in 8 because it has more oxygen. So this is just a way that they've developed to name these or differentiate between the two. So nitrate would be NO3 because it has more oxygen, and 8 tells me that. 8 tells me that that polyatomic ion is going to have more oxygen. Nitrite, NO2, it has one less oxygen, so that's why we end it with ite. The same thing works for sulfate and sulfite. Sulfate is SO4, sulfite is SO3. So sulfate, it ends in 8 because it has one more oxygen than sulfite does. The exact same thing works for phosphite and phosphate. Phosphate has one more oxygen, so that's why it ends in an 8. And phosphite has one less oxygen, so that's how we can identify it as phosphite. So 8s and ites, just try to remember that if it's an 8, if it ends in 8, it has more oxygen. If it ends in ite, it has fewer oxygens. So maybe that will help if you're trying to remember these names for them. And just know that an oxyanion is a polyatomic ion, and so those are the ones that I gave you on this piece of paper that I'm going to ask you about all the time. But they're polyatomic ions, and all it means is there is an element that's bonded with oxygen, so that's it. Pretty simple. Now, I want to move on, and I want to talk about, go back or talk about bonds, or ionic bonds. So we know that these ionic bonds are bonds that are formed by a transfer of electrons. So we have electrons that are actually leaving an atom and moving to another atom, and they're doing that to make a full octet. We want this complete octet, which is right here. So now we've created these ions. Because they're ions, because we've created this sense of attraction. So I have this positive charged element, I have this negatively charged element now, and we know that opposite charges attract one another. So there's something that is keeping them there together right next to one another because now we've created these charges. In terms of that, we know that what keeps the bonds together is the force of attraction, but we have specifically given it a name, which is Coulombic attraction. So just know that Coulombic attraction really just represents the force of attraction between something positively charged and something negatively charged. Now, to go along with that, I still want you to remember or keep thinking about if you add more positive charge, what's going to happen to that attraction between the positives and the negatives? It's going to be even more. That Coulombic attraction is greater because there's more positive charge to pull in those electrons, okay? We also said yesterday that ionic compounds are neutral compounds. So I need to make sure that I balance out these charges to make the overall compound neutral. Now yesterday I think that made a lot more sense or kind of came full circle for us when we saw that we had to write chemical formulas where the charges balanced one another. So we also said that we learned about rules for naming. So I'm not going to go through those because we're going to talk a lot more about those on Monday, and plus we did those yesterday and I felt like you guys were getting it really well. So we'll learn some more naming rules on Monday. But on this one, which I have to stop this because the PowerPoint's going to go crazy. On this slide, we see, or maybe I should say the slide before. So sodium and chlorine. Sodium has one valence electron on its outermost shell, and chlorine only has 7. So sodium is going to give its extra valence electron away because it wants to, because now it's stable because it has this octet. Chlorine's going to gain this extra one, so we're actually transferring an electron from a metal to a non-metal. So this would be an ionic bond. Now that chlorine has this one extra electron, we have to give both of these charges. So since sodium lost an electron, it has more positive charges now than negative charges. So then that means that sodium is going to be a positive 1 charge. Chlorine gained a negative charge, so now it has one more negative charge than it does positive charges, so then that means that chlorine will be negative. So this is a way that we can draw a Lewis dot structure or reaction. But yesterday on your journal, you saw how this is a 1-to-1 ratio, so it's really simple because this is a +1, this is a -1, so it's 1-to-1. But what happens if I have something that has a +3 charge versus a +2 charge? So in this, on your PowerPoint slides, I wanted to give you an example of what would happen in a Lewis dot structure reaction between calcium and phosphorus. Now, you know you could very easily write the chemical formula based on what we did yesterday, and that is I have calcium that has a +2 charge, I have phosphorus which would have a -3 charge, so what do we do with a +2 and a -3? What do we do with those? So we have calcium with a +2, phosphorus with a -3, so it looks like this. We know we have to do the crisscross method. Oh yeah. So we're going to bring that 3 down over by calcium. We're going to bring the 2 down over by phosphorus. So you know that your chemical formula should end up like this. It's calcium phosphide. So Ca3P2. Now, I want to show that, though, using Lewis dot structure. So you know what it should be, and you know the charges of them, but let's just see how the Lewis dot structure works. So calcium wants to get rid of both of these valence electrons. So it can do that because phosphorus needs 3 more, wants to gain 3 electrons. So right now, both of these electrons are going to move over to phosphorus. So now, calcium has a +2 charge because it lost 2 electrons. And now phosphorus, in this case, it has 1, 2, 3, 4, 5, 6, 7. It has 7 electrons. Does it have that full octet? It does not. Does it want to? It absolutely does, because right now then it's still like unstable and it still doesn't like this. So it wants to find some more electrons. Now, all we can do at this point is bond calcium and phosphorus because we're trying to get calcium phosphide. So I'm going to bring in another calcium. Okay, so now I bring in another calcium. It has 2 valence electrons. One of those electrons can go right over here to phosphorus, fill that outer ring. So when we have that, I'm left with this now. Now I have a calcium atom with a +2 charge that's really happy and stable. It has a full octet. I have phosphorus that has all 8 valence electrons around it with a -3 charge. It's completely fine. But now I have this leftover calcium that has 1 valence electron, and it does not want this at all. And not only does it have 1 valence electron, but now it also has a +1 charge. It needs to get rid of this. So to do that, it has to give this away to another phosphorus. This valence electron is now going to go over here to this phosphorus atom. This now becomes a +2 charge because it lost both of its valence electrons. But let's look at phosphorus now. So now I have only one piece that's messed up because these are all balanced and stable. This is the only piece now. So I have 1, 2, 3, 4, 5, 6 atoms, or 6 valence electrons around this atom, around this phosphorus atom. It needs 2 more to have an octet. If it bonds with 1 more calcium atom or calcium ion, those 2 valence electrons can go right down here to this phosphorus atom, which is exactly what it does. In this case, calcium becomes a +2 charge. Phosphorus becomes completely full with its octet with a -3 charge. So all of these are stable, they're happy, we're good. So this is where we can get C3P2, which you already knew how to write that formula based on what we did yesterday. But what I want you to also understand is how these electrons are moving and how they're transferring, because it's really, really important that you understand that phosphorus needed, this last phosphorus maybe needed 1 more valence electron. So calcium's going to come in again, give it 1 electron, but now calcium has this 1 extra electron. So I really want you to understand that process, okay? For ionic compounds, we also can call them another name. The simplest name or the simplest formula for an ionic compound is called a formula unit. So you may see on a quiz or you may hear me ask or for your journal or in your homework,